Close your eyes. Tonight, I want you to imagine something that no human being has ever seen. Something that no camera has ever photographed. Something that exists right now, at this very moment, as you settle into bed and let the weight of the day leave your shoulders. Far from here. Farther than you have ever been from anything. Farther than the moon. Farther than Mars. Farther than Jupiter or Saturn or Neptune or Pluto or any of the icy, nameless objects that drift in the outermost edges of our solar system. Out there, in a darkness so complete that the sun itself has shrunk to just another star, a faint yellow dot no brighter than a candle flame seen from miles away, a small machine is flying through the void. It weighs about as much as a small car. It is roughly the size of a large refrigerator, with a white dish antenna mounted on top that measures about 12 feet across. Attached to its body are long, thin booms that extend outward like the arms of a scarecrow, carrying instruments designed to measure things that no human hand will ever touch. Magnetic fields, charged particles, cosmic rays, the invisible architecture of space itself. It is not accelerating. It has no fuel left for that. No thruster is firing, no engine is running. It simply drifts, carried by the momentum it was given decades ago, coasting through interstellar space at roughly 10.5 miles per second, 17 kilometers per second, about 38,000 miles per hour. That sounds fast. And by the standards of anything you have ever experienced, it is unimaginably fast. At that speed, you could fly from New York to Los Angeles in about 4 minutes. You could circle the entire Earth in just over an hour. It is a speed that makes jet airplanes look like they are standing still. And yet, out here, at the edge of everything, that speed means almost nothing. Because the distances are so vast, so incomprehensibly large, that even traveling at 38,000 miles per hour, this little machine will not reach the nearest star for tens of thousands of years. It is moving at a dead sprint through an emptiness so enormous that it might as well be standing still. This machine has a name. It is called Voyager 1. There is something about that name. Voyager. It comes from an old French word meaning one who makes a journey. Not a tourist, not a visitor. A voyager. Someone who sets out, knowing they may never come back. Someone who leaves the familiar behind and walks into the unknown, not because the unknown is safe, but because remaining behind would be worse. Voyager 1 is the ultimate voyager. It left home nearly 50 years ago, and it has been walking into the unknown ever since. Every day it moves farther from everything it has ever known. Every day the sun grows a little fainter in its rearview mirror, if it had one. Every day the silence around it deepens. And no one is driving. No one is steering. No human hand is at the controls. Voyager 1 is alone, in the most complete sense of the word. It is the loneliest object that has ever existed. And right now, at this very moment, Voyager 1 is the farthest human-made object from Earth. Nothing we have ever built, nothing we have ever touched, nothing we have ever launched has traveled as far as this small, quiet spacecraft. It is more than 15 billion miles from home, more than 160 times the distance from the Earth to the Sun. So far away that the signals it sends back, traveling at the speed of light, the fastest speed anything in the universe can travel, take more than 22 hours to reach us. When mission controllers at the Jet Propulsion Laboratory in Pasadena, California, send a command to Voyager 1, they must wait nearly 2 full days for a response. A simple question and answer, a ping, and its echo takes almost 45 hours. Think about that for a moment. You could fall asleep, wake up, live an entire day, fall asleep again, and still be waiting for Voyager's reply. And that distance is growing. Every second that passes, Voyager 1 moves another 10.5 miles farther from Earth. Another 10.5 miles deeper into the dark. It will never stop. It will never slow down. There is nothing out there to slow it down. No air, no friction, no resistance of any kind. Just the emptiness of interstellar space, a vacuum so pure that you could travel for billions of miles without encountering a single atom. Voyager 1 has been out there for nearly half a century, and it will continue out there for a very, very long time. Long after its instruments fall silent. Long after its nuclear power source decays to nothing. Long after the last faint signal fades to static and the engineers who built it are dust. Voyager 1 will keep moving. A ghost ship in the cosmic ocean, carrying a message from a species that may or may not still exist by the time anyone finds it. Tonight, we are going to follow that little machine, not just to where it is now, but to where it is going. We are going to trace its path forward through time, not years or centuries, but thousands of years. Hundreds of thousands of years. 1,000,000 years. We are going to ask a question that stretches the imagination to its breaking point. Where will Voyager 1 be in 1,000,000 years? It is the kind of question that makes you dizzy if you think about it long enough. 1,000,000 years. A time scale so vast that it dwarfs everything in human experience. 1,000,000 years ago, modern humans did not exist. The species Homo sapiens had not yet evolved. Our ancestors were different creatures, walking upright on the African savanna, using simple stone tools, living in a world of ice ages and megafauna that has long since vanished. Everything you have ever known, every civilization, every language, every empire, every war, every love story, every piece of music, every mathematical theorem, every child who has ever been born, all of it fits inside the last few thousand years. The last flicker, the last breath, the last heartbeat of 1,000,000-year span. And Voyager 1 will still be out there, drifting, silent, carrying its golden record like a letter in a bottle thrown into an ocean with no shore. But before we follow it forward, let us go back. Let us return to the beginning. To a warm September day in 1977, when a small group of engineers and scientists stood in a control room in Florida and watched a rocket climb into the sky, carrying a machine that would travel farther than anything they had ever imagined. Let us go back to the day we let go. Before we continue, I want to take a moment. If you enjoy falling asleep to these journeys through the cosmos, consider subscribing to the Science Pillow. Every week, a new documentary arrives, designed to carry you gently through the wonders of the universe and into a peaceful sleep. All you need to do is press the subscribe button, and the stars will be waiting for you every night. You do not need to stay awake. You do not need to take notes. Just lie back, close your eyes, and let the universe do the rest. Now, let us begin at the beginning. Section 2. The Day We Let Go. To understand where Voyager 1 is going, you first need to understand where it came from. And to understand where it came from, you need to understand the time it was born in. Because Voyager 1 is a child of the 1970s, an era that shaped everything about the spacecraft, from its technology to its mission to the dreams it carried. The 1970s were a strange and fertile time for space exploration. The Apollo program had ended. The last astronaut had left the moon in December of 1972, and the great adventure that had defined the 1960s was over. The public had moved on. The budgets had been cut. The enormous Saturn V rockets that had carried humans to the moon were being retired, their remaining hardware sent to museums where schoolchildren would stare up at them and try to imagine what it must have been like. But within NASA, within the Jet Propulsion Laboratory in Pasadena, California, within the small, dedicated community of planetary scientists and engineers who had spent their careers studying the planets from afar, there was a different feeling. A feeling that the real work was just beginning. Because while the astronauts had been going to the moon, the robotic explorers had been going everywhere else. Mariner spacecraft had flown past Mercury, Venus, and Mars. Pioneer probes had ventured to Jupiter and Saturn, sending back the first close-up images of those giant worlds. And now, a new generation of spacecraft was being designed, more capable, more sophisticated, more ambitious than anything that had come before. Voyager was the crown jewel of this new generation, and its story begins with an alignment of planets that had not occurred since the time of Thomas Jefferson. On September 5, 1977, a Titan 3E Centaur rocket lifted off from Launch Complex 41 at Cape Canaveral, Florida. It was a warm, humid morning on the Florida coast, the kind of day where the air itself seems to shimmer. The rocket rose slowly at first, balanced on a column of white-orange flame, and then accelerated, punching through the scattered clouds and climbing toward the blue-black edge of the atmosphere. Strapped to the top of that rocket was a spacecraft that had taken years to design and build. It was not especially large. It weighed roughly 1,820 pounds, about the weight of a compact car. Its body was a 10-sided aluminum frame, about the size of a large kitchen table, packed with instruments, circuit boards, and wiring that had been assembled with a precision that bordered on obsessive. Everything had to work. Everything had to survive the launch. And everything had to keep working for years, possibly decades, in conditions that would destroy almost any piece of equipment on Earth. This spacecraft was Voyager 1, and its twin, Voyager 2, had actually launched 16 days earlier, on August 20th. Despite being called Voyager 2, it launched first. The naming was based on trajectory, not launch order. Voyager 1 would travel a faster path and would overtake its sibling, arriving at Jupiter first. Hence the name. The Voyager program had its roots in a remarkable alignment of the outer planets that occurs only once every 175 years. In the late 1960s, an aerospace engineer at the Jet Propulsion Laboratory named Gary Flandreau discovered that Jupiter, Saturn, Uranus, and Neptune would be arranged in a geometric configuration in the late 1970s and early 1980s that would allow a single spacecraft to visit all 4 planets, using the gravity of each one to sling itself onward to the next. This alignment, sometimes called the Grand Tour, was a cosmic coincidence so rare that it would not happen again until the 22nd century. The original Grand Tour concept was ambitious and expensive, involving large, complex spacecraft that could survive the entire journey. But budget constraints forced NASA to scale back the plan. Instead of one grand mission, they designed 2 simpler spacecraft, each initially approved to visit only Jupiter and Saturn. The possibility of continuing to Uranus and Neptune was built into the design, but not officially funded or promised. The engineering behind the Voyager spacecraft is a story of extraordinary ingenuity and careful compromise. In the 1970s, the computers that guided these machines were less powerful than a modern pocket calculator. Voyager's onboard computer, the Computer Command Subsystem, had about 69 kilobytes of memory. Not megabytes, not gigabytes. 69 kilobytes. Your smartphone has roughly 1,000,000 times more computing power than the machine that is currently the farthest human-made object from Earth. And yet, that tiny computer was enough. Because the engineers who designed Voyager were not trying to build a general-purpose machine. They were building a spacecraft with a very specific set of tasks, and every byte of memory, every line of code, was dedicated to exactly those tasks and nothing more. The software could be updated from Earth, reprogrammed as needed, patched and modified even after the spacecraft was billions of miles away. Over the decades, engineers at the Jet Propulsion Laboratory have rewritten Voyager's software many times, finding ways to squeeze more capability out of hardware that was designed before the first personal computers existed. The instruments aboard Voyager 1 were a carefully chosen suite of sensors designed to study the planets and their moons in ways that had never been possible before. There were cameras, 2 of them, a wide angle and a narrow angle, capable of capturing images with a resolution that was revolutionary for the time. There was an infrared spectrometer for measuring temperatures and atmospheric compositions, an ultraviolet spectrometer for studying upper atmospheres and auroras, a magnetometer for mapping magnetic fields, plasma and charged particle detectors for studying the solar wind and the radiation environments around the giant planets, a cosmic ray detector, and a planetary radio astronomy receiver for listening to the natural radio emissions of planets. Each of these instruments drew power from a source that is one of the most remarkable aspects of the Voyager design. Because out at Jupiter and beyond, the sun is too faint to power solar panels effectively. At Jupiter's distance, sunlight is only about 4% as intense as it is at Earth. At Saturn, it drops to roughly 1%. Solar power, which works beautifully for spacecraft in the inner solar system, is essentially useless in the outer reaches. The Voyager engineers needed a different solution. They chose nuclear power. Specifically, they used radioisotope thermoelectric generators, or RTGs. 3 of them, mounted on a long boom extending away from the spacecraft's body to minimize interference from their radiation with the sensitive instruments. Each RTG contained a cylinder of plutonium-238, a radioactive isotope that generates heat as it decays. That heat was converted into electricity using thermoelectric materials, substances that produce a voltage when one side is hotter than the other. When Voyager 1 launched, its 3 RTGs produced about 470 watts of electrical power. That is roughly enough to power 4 or 5 household light bulbs. The entire Voyager spacecraft, with all its instruments, its computers, its radio transmitter, its heaters and actuators and motors, ran on less power than it takes to run a hairdryer. And the engineers made it work. They made it work brilliantly. But plutonium-238 has a half-life of about 87.7 years. This means that every 87.7 years, half of the remaining plutonium decays, and the power output drops accordingly. By the time you are hearing this, nearly 5 decades after launch, Voyager 1's RTGs are producing only about 220 watts, and that number is still falling. Every year, the power drops by roughly 4 watts. The spacecraft is slowly, inexorably, running out of electricity. Think about that for a moment. The power source that has kept Voyager alive for nearly 5 decades is a few cylinders of radioactive metal, slowly decaying, atom by atom, converting mass into heat and heat into the tiny trickle of electricity that keeps the spacecraft's heart beating. It is one of the most elegant power sources ever designed. No moving parts, no fuel to burn, no chemical reaction to exhaust. Just the quiet, inevitable decay of unstable nuclei, a process as old as the elements themselves, harnessed to power a machine at the edge of the solar system. And now that power is fading. Like a campfire burning down in the small hours of the morning, the glow is dimming. The warmth is retreating. The light is going out. To conserve what remains, NASA has been systematically shutting down instruments and heaters aboard Voyager 1, one by one, like a family in a cold house turning off the lights in rooms they no longer use. The cameras were turned off long ago, back in 1990, after Voyager took its famous pale blue dot photograph. Several scientific instruments have been deactivated. Heaters that kept certain components warm have been switched off, allowing parts of the spacecraft to cool to temperatures that were never tested during its design. And still, the engineers have kept the most essential systems running, squeezing every last watt from the decaying plutonium to maintain contact with a machine that is farther from home than anything humanity has ever built. By the mid-2030s, probably around 2036 or 2037, the power will drop below the level needed to operate any scientific instruments at all. Shortly after that, the transmitter will fall silent. The last faint signal from Voyager 1 will fade into the background noise of the cosmos, and for the first time in nearly 6 decades, there will be no way to communicate with the spacecraft. It will still be out there, still moving, still carrying its cargo, but it will be deaf and mute, a silent traveler in an ocean of silence. But we are getting ahead of ourselves. Before Voyager 1 fell silent, before it crossed the boundary of the solar system into interstellar space, before it became the loneliest object ever made, it did something extraordinary. It visited the giant planets. And what it found there changed everything we thought we knew about our solar system. Let us slow down. Let us take our time with this part of the story. Because the Voyager encounters with Jupiter and Saturn are among the greatest achievements of the space age, and they deserve to be savored. They are the reason Voyager exists. They are the purpose for which it was built. And the discoveries it made at those 2 giant worlds transformed our understanding of the solar system more profoundly than perhaps any other space mission in history. So settle in. Let your breathing find its natural rhythm. And let us travel together to the giant planets. Section 3. The Grand Tour. There is something almost magical about the concept of the Grand Tour. The idea that the planets, in their slow, independent orbits around the Sun, occasionally line up in a configuration that allows a single spacecraft to visit them all, one after another, using the gravity of each planet to bend its path and fling it onward to the next. It is as if the solar system, for a brief window of time, opens a highway through its outer reaches, a corridor that exists for only a few years before the planets drift apart and the window closes, not to open again for nearly 2 centuries. This alignment was not designed. It was not planned. It is simply a consequence of the mathematics of orbital mechanics, the fact that planets orbit at different speeds and different distances, and that occasionally, by sheer coincidence, Their positions create a pathway that a fast-moving spacecraft can follow. It is like catching a series of green lights on a long highway. Miss one, and you have to wait. Gary Flandreau, the engineer who discovered the alignment, recognized that it was an opportunity that could not be wasted, and NASA, despite the budget cuts and the post-Apollo malaise, recognized it too. The result was the Voyager program. 2 spacecraft, 2 chances. 2 small machines that would ride the grand tour alignment to the outermost planets, and then, if all went well, continue on into interstellar space. Voyager 1 took the fast path, and its first stop was Jupiter. Voyager 1 reached Jupiter on March 5, 1979, after a journey of about 18 months. As the spacecraft approached, its cameras began capturing images of the giant planet that were unlike anything astronomers had seen before. From Earth, Jupiter appears as a bright, steady point of light in the night sky. Sometimes the brightest object in the heavens after the Moon and Venus. Through a backyard telescope, you can make out the banded structure of its cloud tops and perhaps a handful of its largest moons. But from Voyager's perspective, closing in at tens of thousands of miles per hour, Jupiter transformed from a point of light into a world. And what a world it was! Jupiter is the largest planet in our solar system. It is so large that you could fit more than 1,300 Earths inside it. Its diameter is roughly 86,881 miles, about 11 times the diameter of Earth. If Earth were a grape, Jupiter would be a basketball. It is a gas giant, meaning it has no solid surface. What you see when you look at Jupiter is not land or ocean, but the tops of an atmosphere that extends downward for thousands of miles, growing denser and hotter with depth, until the hydrogen gas is compressed so intensely that it becomes a liquid, and then, deeper still, a metallic fluid that conducts electricity and generates Jupiter's immense magnetic field. The Great Red Spot, Jupiter's most famous feature, had been observed by astronomers for centuries, but Voyager revealed it in stunning detail for the first time. It is a storm, an anticyclonic storm, a high-pressure system rotating counterclockwise in Jupiter's southern hemisphere. And it is enormous. At the time of Voyager's flyby, the Great Red Spot was large enough to swallow 2 or 3 Earths side by side. It has been raging for at least 350 years, possibly much longer. No one knows exactly how old it is or what sustains it. It simply spins, vast and patient, year after year, century after century, a storm older than any nation on Earth. Voyager's cameras captured the swirling, turbulent atmosphere of Jupiter in a level of detail that left scientists breathless. The banded structure, visible even from Earth, resolved into an incredibly complex system of jet streams, eddies, and vortices. The cloud bands are driven by Jupiter's rapid rotation. Despite being 11 times wider than Earth, Jupiter completes a full rotation in just under 10 hours. That furious spin stretches the atmosphere into parallel bands that race around the planet at hundreds of miles per hour, with winds at the boundary between adjacent bands creating violent shear zones where storms are born and devoured. But the real surprise was not Jupiter itself. It was the moons. Before Voyager arrived, most scientists expected Jupiter's moons to be dead, frozen, cratered worlds. They expected them to look something like our own moon, pockmarked by billions of years of impacts, geologically inert, their surfaces unchanged since the early solar system. The moons were interesting primarily as curiosities, as stepping stones in our understanding of the solar system's formation, not as worlds in their own right. Voyager shattered that expectation entirely. What it found was not a collection of dead rocks orbiting a giant planet. What it found was a miniature solar system, a family of worlds, as diverse and as dynamic as anything in the inner solar system, each one a revelation, each one a shock. Jupiter has a vast family of moons. As of the most recent count, more than 95 have been identified, but the four largest, the ones discovered by Galileo Galilei in 1610, when he pointed his homemade telescope at Jupiter and saw four tiny points of light moving around the planet from night to night, are in a class by themselves. They are called the Galilean moons, Io, Iao, Europa, U-Rho-H-P, Ganymede, Gan-E-Mede, and Callisto, Ku-Listo. Each one is a world unto itself, and Voyager 1 revealed each of them in ways that no one had anticipated. Io was the first shock. As Voyager approached, navigation engineer Linda Morabito was examining an image of Io taken against the blackness of space, looking for background stars that could be used to calculate the spacecraft's precise position. Instead, she noticed something unusual on the limb of the moon, a bright, crescent-shaped plume rising above the surface. It was an eruption, a volcanic eruption, on Io, a moon that, based on everything scientists thought they knew, should have been a cold, dead, cratered ball of rock. Instead, Io turned out to be the most volcanically active body in the entire solar system. Voyager discovered at least 9 active volcanoes during its flyby, with plumes of sulfur and sulfur dioxide rising hundreds of miles above the surface. The entire moon was being turned inside out by tidal forces. Jupiter's immense gravity, combined with the gravitational tug of the other large moons, flexes and kneads Io's interior, generating tremendous heat through friction. That heat melts rock deep inside the moon and drives it to the surface in continuous volcanic eruptions. The surface of Io is a hellscape of yellows, oranges, reds, and blacks, painted by sulfur compounds ejected from its volcanoes. There are no impact craters visible on Io's surface, because the constant volcanic resurfacing buries them as fast as they form. The entire surface is recycled on a timescale of perhaps 1,000,000 years or less. It is a world in constant transformation, perpetually remaking itself, a moon that looks more like a pizza than a planet, as one scientist famously quipped. The discovery of active volcanism on Io was one of those moments in science that reshapes your understanding of the universe. Before Voyager, we thought we understood how the solar system worked. Rocky bodies lose their internal heat over time. Small ones cool fast. Large ones cool slowly. But eventually, they all cool. They all become geologically dead. The Moon, Mercury, Mars, all had been active once in their youth, but all had quieted as their interiors cooled and solidified. A moon the size of Io, smaller than our own moon, should have been cold and dead for billions of years. But the scientists had forgotten about tides, not ocean tides, the kind you see at the beach, gravitational tides. The stretching and compressing of an entire world by the gravitational pull of a nearby giant planet. Jupiter's gravity kneads Io like dough, flexing its rocky interior back and forth with every orbit, generating heat through friction at a rate that more than compensates for the heat the small moon would otherwise lose to space. Io is being cooked from the inside, and the volcanoes are the result. Pressure valves releasing the pent-up heat in spectacular eruptions that paint the surface in sulphurous yellows and reds. It was a lesson in humility. The solar system had surprises that no one had anticipated, and Voyager was about to deliver another one. Europa was quieter, but in some ways more astonishing. Voyager's images revealed a moon covered in smooth white ice, crisscrossed by a network of dark, reddish-brown lines that stretched across its surface like cracks in an eggshell. There were almost no impact craters, which meant the surface was young, constantly being renewed. But unlike Io, there were no volcanoes. Something else was resurfacing Europa, something from below. Scientists quickly realized what it might be. Beneath Europa's icy shell, there was almost certainly a global ocean of liquid water. The dark lines on the surface were fractures in the ice, created by tidal flexing similar to what drives Io's volcanism, but less extreme. Through these cracks, warmer material from below welled up and refroze, creating the intricate pattern of ridges and grooves that Voyager photographed. A global ocean. Liquid water. Beneath the ice of a moon more than 400 million miles from the sun. The implications were staggering. Where there is liquid water, there is the possibility of life. Not the kind of life we see on the surface of Earth, basking in sunlight and breathing air, but something deeper, something older, something that might thrive in the dark, warm waters beneath Europa's frozen shell, fed by chemical energy from hydrothermal vents on the ocean floor, living in conditions not unlike those found at the bottom of Earth's own oceans. Voyager's brief flyby of Europa raised a question that scientists are still working to answer, decades later. Is there life beneath the ice of Europa? We do not know, but we know the question is worth asking. And we know that without Voyager, we might never have thought to ask it. Let that sink in for a moment. A spacecraft that was designed to photograph planets and study atmospheres accidentally discovered what may be the most promising habitat for extraterrestrial life in our solar system. A hidden ocean, warmed by tidal forces, shielded from radiation by a thick shell of ice, potentially rich in the chemical ingredients that life needs to emerge and thrive. And all of it orbiting a gas giant that is more than 400 million miles from Earth. Before Voyager, the search for life beyond Earth was focused almost entirely on Mars. After Voyager, the Tho-ite solar system suddenly seemed full of possibilities. Oceans hidden beneath icy shells, volcanic vents heating alien seafloors. Chemistry happening in places where no one expected chemistry to happen. The universe, it seemed, was more creative than we had given it credit for. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, revealed a surface divided into two distinct types of terrain. Old, dark, heavily cratered regions, and younger, lighter, grooved terrain that suggested tectonic activity at some point in the moon's past. Callisto, the outermost of the 4 Galilean moons, was ancient and battered, its surface saturated with craters, a frozen record of billions of years of bombardment. Together, the 4 Galilean moons presented a remarkable spectrum of geological activity, from the volcanic fury of Io to the frozen stillness of Callisto, all orbiting the same planet, all shaped by the same gravitational forces, but each responding in its own unique way. Voyager 1 made its closest approach to Jupiter on March 5, 1979, passing within 128,400 miles of the cloud tops. During the encounter, the spacecraft used Jupiter's gravity to change its trajectory, bending its path and accelerating it toward its next target. This is called a gravity assist, and it is one of the most elegant techniques in space exploration. By flying close to a massive planet at precisely the right angle and speed, a spacecraft can steal a tiny amount of the planet's orbital energy, gaining speed without using any fuel. Jupiter barely notices the exchange. The planet's orbit changes by an amount so small it cannot be measured. But for the spacecraft, the boost is dramatic. Voyager 1 left Jupiter traveling significantly faster than it arrived, flung outward like a stone from a sling, aimed at Saturn. The gravity assist is worth pausing on, because it illustrates something beautiful about physics. The energy Voyager gained did not come from nowhere. It came from Jupiter. The spacecraft, by flying past Jupiter at the right angle, transferred a tiny, immeasurably small amount of Jupiter's orbital momentum to itself. Jupiter slowed down by a fraction so infinitesimal that it could never be detected, and Voyager sped up by thousands of miles per hour. It is like a ping-pong ball bouncing off a moving freight train. The train does not notice, but the ping-pong ball is sent flying. This technique, first proposed by the mathematician Michael Minovich in 1961, revolutionized space exploration. Before the gravity assist, visiting the outer planets required enormous rockets and vast amounts of fuel. With the gravity assist, the planets themselves became the fuel. Each one a stepping stone, each one a boost, each one lending a tiny fraction of its vast momentum to a small machine passing through its gravitational field. It is one of the most elegant ideas in the history of space travel, and Voyager used it to perfection. Let your thoughts drift for a moment. Imagine the darkness of space between Jupiter and Saturn, a gulf of more than 400 million miles. Voyager crossed it in about 20 months, its cameras turned off to conserve power and data storage, its instruments quietly measuring the solar wind and cosmic rays, the spacecraft tumbling slowly through the void with nothing around it but emptiness and starlight. And then, in November of 1980, Saturn appeared. At first, it was just a bright point of light among the stars, no different from how it appears to your eyes on a clear night. But, as the weeks passed and Voyager drew closer, the point of light began to resolve. First, the disk of the planet itself, a pale, buttery yellow, significantly less colorful than Jupiter's wild bands of orange and brown and white. Then the rings, emerging from the planet's equator like a thin line at first, and then, as the geometry shifted with Voyager's approach, widening into the magnificent, gravity-defying structure that has captivated human beings since Galileo first glimpsed it through his crude telescope in 1610, and could not figure out what he was seeing. Galileo thought Saturn had ears, or handles, or perhaps was a triple planet. His telescope was too primitive to resolve the rings for what they were. It took another 45 years before Christian Huygens, using a better instrument, correctly identified the rings as a flat disk encircling the planet, tilted at an angle to our line of sight. And it would take another 320 years before Voyager 1 showed us what the rings really look like, up close, in all their intricate, breathtaking beauty. If Jupiter is the king of the planets, Saturn is the jewel. There is no sight in the solar system more beautiful than Saturn and its rings, seen up close. And Voyager 1 was the first spacecraft to show them to us in their full, breathtaking glory. Saturn's ring system is one of the most visually stunning structures in nature. From Earth, even through a modest telescope, the rings are visible as a bright, flat disk encircling the planet, tilted at an angle that changes over Saturn's 29-year orbit. They look solid and smooth. But Voyager revealed that they are anything but. The rings are made of billions upon billions of individual particles, ranging in size from tiny grains of sand to chunks of ice as large as houses. Each particle orbits Saturn independently, like a tiny moon, held in place by the planet's gravity and sculpted into intricate patterns by the gravitational influence of Saturn's many moons. Voyager's cameras revealed that what had appeared from Earth as a handful of broad, smooth rings was actually a system of thousands of individual ringlets, separated by gaps of varying widths, arranged in a pattern of almost hypnotic complexity. Some of the gaps were caused by the gravitational influence of small moons orbiting within the ring system, sweeping up particles and creating clear lanes like a plow cutting through snow. Others were caused by orbital resonances, regions where the orbital period of ring particles matched a simple fraction of the orbital period of one of Saturn's larger moons, creating gravitational perturbations that cleared the particles away over time. The rings are extraordinarily thin compared to their width. They stretch outward from Saturn for nearly 282,000 miles, but their thickness is typically only about 30 feet. If you could shrink the rings down to the size of a football field, they would be thinner than a sheet of paper. They are a structure of almost impossible flatness, a razor-thin disk of ice and rock encircling a world that is 9.5 times wider than Earth. And the rings are not permanent. This is something that scientists have come to understand more fully in the decades since Voyager's visit. The rings are slowly raining down onto Saturn's atmosphere, pulled inward by gravity and eroded by complex interactions with Saturn's magnetic field and upper atmosphere. At their current rate of decay, the rings may be gone entirely in 100 million to 300 million years. That sounds like a long time, but Saturn is 4.5 billion years old. The rings may be a relatively recent phenomenon, perhaps only 100 million to 200 million years old. They may have formed from the breakup of a moon or comet that ventured too close to Saturn's gravitational embrace and was torn apart by tidal forces. This means that we are lucky. We happen to exist at a moment in the solar system's history when Saturn has its rings. Beings who lived on Earth during the age of the dinosaurs may have looked up and seen a ringless Saturn, just another bright point of light among the wandering stars. And beings who live on Earth, or wherever we have gone, 1 billion years from now will see a Saturn without rings, its most beautiful feature dissolved and absorbed, a jewel stripped of its setting. We are witnessing something fleeting, something ephemeral, something beautiful precisely because it will not last. And Voyager 1 captured it in hundreds of photographs at a resolution that brought tears to the eyes of the scientists who first saw them. But Voyager's most consequential discovery at Saturn was not the rings. It was a moon called Titan. Titan is Saturn's largest moon, and the second largest moon in the solar system after Jupiter's Ganymede. It is the only moon in the solar system with a thick, substantial atmosphere. And it was this atmosphere that changed everything. Before Voyager arrived, scientists knew that Titan had an atmosphere. Ground-based observations had detected the spectral signature of methane in its gaseous envelope. But no one knew how thick the atmosphere was or what it looked like beneath the orange haze. Voyager 1 was targeted to fly very close to Titan, passing within just 4,000 miles of its surface, specifically to study this mysterious world. What Voyager found was astonishing. Titan's atmosphere was not thin and wispy like the atmospheres of other moons. It was thick, very thick. The surface pressure on Titan turned out to be roughly 50% higher than the surface pressure on Earth. If you could stand on Titan's surface, you would feel the weight of 50% more atmosphere pressing down on you than you do right now. And the atmosphere was composed primarily of nitrogen, the same gas that makes up 78% of Earth's atmosphere. The rest was methane and trace amounts of other hydrocarbons. This was extraordinary. Here was a moon, orbiting a planet nearly 1 billion miles from the Sun, with an atmosphere denser and more Earth-like in composition than any other body in the solar system besides Earth itself. The orange haze that shrouded Titan was a photochemical smog, produced when ultraviolet light from the distant Sun broke apart methane molecules in the upper atmosphere, and the fragments recombined into complex organic compounds called tholins that drifted downward like a constant, gentle rain. Voyager's cameras could not see through the haze. The surface of Titan remained hidden, an orange mystery. But scientists suspected, based on the temperature and pressure data, that Titan's surface might harbor lakes or even seas of liquid methane and ethane, hydrocarbons that are gases on Earth but liquids on Titan, where the surface temperature is roughly minus 179 degrees Celsius. A world with weather, with rain, with rivers and lakes. But instead of water, the fluid is methane. Instead of rocks, the ground might be made of water ice as hard as granite at those temperatures. This discovery made Titan one of the most intriguing worlds in the solar system. It was a place where chemistry was doing something extraordinary, building complex organic molecules in quantities that made the entire moon a kind of prebiotic laboratory, running experiments in organic chemistry on a planetary scale. Not life, as far as we know, but the ingredients of life, the raw materials assembled and mixed and transformed by cold, slow, patient chemistry over billions of years. There was a cost to this discovery. By choosing to fly close to Titan, Voyager 1's trajectory was bent sharply northward, out of the plane of the solar system. This meant that Voyager 1 could not continue to Uranus and Neptune. The Titan flyby was a one-way decision. Once Voyager 1 swung past Titan, its path was fixed. It would leave the solar system heading upward, away from the plane where the planets orbit, climbing toward the constellation Ophiuchus and, eventually, the stars. Voyager 2, its twin, would take the alternate path. Voyager 2 bypassed Titan and continued onto Uranus in 1986 and Neptune in 1989, completing the grand tour that the Voyager program had been designed for. But Voyager 1's journey through the planetary system was over. After Saturn, after Titan, there were no more worlds to visit, just the long, slow coast outward, into the dark. And it is worth pausing here to acknowledge the cost of that decision, because it was a genuine sacrifice. The Titan flyby gave us invaluable data about one of the most mysterious worlds in the solar system. But it meant that Voyager 1 would never see Uranus's tilted axis and strange dark rings. It would never photograph Neptune's cobalt blue atmosphere and the Great Dark Spot. It would never encounter Triton, Neptune's giant moon, with its geysers of nitrogen ice and its retrograde orbit that suggests it was once a wanderer from the Kuiper Belt, captured by Neptune's gravity long ago. All of those discoveries fell to Voyager 2, which took the longer, slower path and completed the grand tour in 1989, 12 years after launch. But Voyager 1 had earned its rest from planetary encounters. It had shown us things no human eye had ever seen, and it had one more photograph to take, one more act before it turned its cameras off forever. But Voyager 1 had one more photograph to take, one more act before it turned its cameras off forever. On February 14th, 1990, when Voyager 1 was about 3.7 billion miles from Earth, beyond the orbit of Neptune, mission controllers sent a command to turn the spacecraft around and photograph the planets it was leaving behind. The resulting series of images, taken from a distance that no camera had ever achieved before, became known as the family portrait. 60 frames stitched together, showing 6 of the 9 planets scattered like tiny dots across a vast, dark canvas. But one image from that series became something more, something that transcended science and entered the realm of philosophy. In one of the frames, barely visible against the glare of scattered sunlight, was a tiny, pale blue speck, a fraction of a pixel, almost lost in the noise. That speck was Earth. The astronomer Carl Sagan, who had been one of the driving forces behind the Voyager program and who had personally advocated for taking that photograph, wrote about it in words that have been quoted more than perhaps any other passage in the history of astronomy. Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. After the pale blue dot photograph, the cameras were turned off. Voyager 1's imaging system was shut down to save power. The spacecraft would never take another picture. From that point forward, it flew blind, sensing the universe through its other instruments, measuring fields and particles and radiation, but never again looking with eyes that could see. And so it flew on, outward, into the dark, toward the edge of everything. For the next 22 years, Voyager 1 flew in silence. Or rather, it flew without eyes. Its other instruments continued to operate, measuring the solar wind, counting cosmic rays, mapping the sun's magnetic field as it stretched thinner and thinner with distance. The data it sent back was not dramatic. There were no photographs of swirling storms or volcanic moons, just numbers. Columns of numbers, transmitted at the painfully slow rate of 160 bits per second, traveling at the speed of light across the growing void, arriving at Earth's largest radio dishes as whispers so faint that they had to be plucked from the cosmic background noise by some of the most sensitive receivers ever built. But those numbers told a story of a spacecraft slowly approaching a boundary that no one had ever crossed. A boundary where the sun's influence ends and the galaxy begins. Section 4. The Edge of Everything. To understand where Voyager 1 went after its cameras fell silent, you need to understand what the edge of the solar system actually means. Because the solar system does not have a clean, sharp boundary. There is no line painted on the void, no fence, no wall. The transition from inside to outside is gradual, blurred, and defined differently depending on what you choose to measure. The simplest way to think about the solar system is the region dominated by the sun's gravity. By that measure, the solar system extends fantastically far out to the Oort cloud, a vast spherical shell of icy bodies that surrounds the sun at distances of perhaps 2,000 to 100,000 astronomical units. 1 astronomical unit is the distance from the Earth to the sun, about 93 million miles. So the outer edge of the Oort cloud may be nearly 100,000 times farther from the Sun than the Earth is. At that distance, the Sun's gravity is still strong enough to hold icy bodies in loose, slow orbits, but only barely. The gravitational pull of passing stars and the tidal forces of the galaxy itself can nudge these objects out of their orbits, sending some of them plunging inward toward the Sun as long-period comets, and others drifting away into interstellar space forever. Voyager 1 has not yet reached the Oort cloud, not even close. At its current distance of roughly 165 astronomical units from the Sun, Voyager has barely left the Sun's doorstep by Oort cloud standards. It will not enter the inner edge of the Oort cloud for roughly another 300 years, and it will not exit the outer edge of the Oort cloud for perhaps another 30,000 years. For all its speed, for all the decades of travel, Voyager 1 is still deep inside the Sun's gravitational domain. But there is another boundary, a different kind of edge, not gravitational but physical. It is defined not by gravity but by the solar wind, the constant stream of charged particles that flows outward from the Sun in all directions at speeds of roughly 1 million miles per hour. The Sun is not just a ball of light. It is a star, and, like all stars, it is constantly shedding material into space. The solar wind is a flow of protons and electrons, stripped from hydrogen atoms in the Sun's outer atmosphere, the corona, and flung outward by the tremendous heat and magnetic forces at the solar surface. This wind is not gentle. It is a supersonic plasma, a river of charged particles racing outward at hundreds of kilometers per second, carrying the Sun's magnetic field with it like a net dragged through water. As the solar wind flows outward, it inflates a vast bubble in interstellar space. This bubble is called the heliosphere. Inside the heliosphere, the dominant medium is the solar wind. The particles you encounter are particles from the Sun. The magnetic field is the Sun's magnetic field, stretched and twisted and carried outward by the flowing plasma. Inside the heliosphere, you are, in a very real sense, inside the Sun's atmosphere. You are bathed in the Sun's breath. But the heliosphere is not infinite. The solar wind, powerful as it is near the Sun, weakens with distance. As it spreads out over an ever larger sphere, its density and pressure decrease. Eventually, at a great distance from the Sun, the outward pressure of the solar wind drops to the point where it can no longer push back against the pressure of the interstellar medium, the thin gas and dust that fills the space between the stars. At that boundary, the solar wind slows from supersonic to subsonic speeds, piles up, and eventually stops. This boundary is called the heliopause. The heliopause is, in a meaningful sense, the true edge of the Sun's atmosphere. Inside it, you are inside the Sun's domain. Outside it, you are in interstellar space, in the space between the stars, in the void. And it was this boundary that Voyager 1 crossed in 2012. Before we talk about the crossing itself, let us take a moment to appreciate what it means to stand at the edge of the heliosphere, if standing were possible in such a place. Imagine yourself there at the heliopause, roughly 122 astronomical units from the Sun, 11 billion miles from home. The Sun is still visible, a bright star, brighter than any other star in the sky, but no longer the blazing disk you know from Earth. It is a point of light. Brilliant, yes, but a point. You could blot it out with your thumb held at arm's length. And all around you, in every direction, stars fill the sky. Not just the familiar constellations, which would look almost exactly the same from this distance because the stars that form them are so much farther away, but a richness, a density of starlight that would make the sky feel full. Because out here there is no atmosphere to scatter light, no city, glow to wash out the faintest stars. The sky is black and brilliant and impossibly deep. And somewhere in that blackness, invisible to any eye, a boundary exists. On one side, the sun's wind still flows, still pushes, still carries the sun's magnetic field outward. On the other side, the interstellar medium reigns. Different particles, different magnetic fields, different origins, a different ocean. Voyager 1 approached that boundary slowly over years, and then it crossed. The crossing was not sudden. It was a gradual transition that scientists debated for months. In the years leading up to the crossing, Voyager 1's instruments detected a series of changes in its environment. The density of charged particles from the sun began to decrease. The density of cosmic rays, high-energy particles from outside the solar system, began to increase. The magnetic field shifted. The plasma environment changed. On August 25, 2012, Voyager 1's instruments recorded a dramatic and permanent change. The density of solar wind particles dropped to near zero. The density of interstellar cosmic rays jumped sharply. The magnetic field changed character, becoming smoother and more uniform, consistent with what scientists expected from the interstellar medium. After years of anticipation and months of uncertainty, NASA officially announced in September 2013, after careful analysis of the data, that Voyager 1 had crossed the heliopause and entered interstellar space. It was the first human-made object ever to do so. The news spread slowly, carefully, because the scientists wanted to be absolutely certain before making the announcement. The data was examined and re-examined. Alternative explanations were considered and ruled out. The scientific paper was reviewed by independent experts. And then, on September 12, 2013, more than a year after the actual crossing, NASA held a press conference and told the world. Voyager 1 had left the building. It was in interstellar space. For the first time in the 4.5 billion-year history of our solar system, something from inside had crossed the boundary and entered the space beyond. The moment was historic. And yet, to the public, it was strangely quiet. There were no parades, no speeches by presidents, no live television coverage watched by millions. A few news articles, a few social media posts, a brief flurry of interest, and then the world moved on to other things. Perhaps this is because the crossing was invisible. There was nothing to see. No photograph of a boundary being crossed. No dramatic fireworks or celebration. Just numbers on a screen, measurements of plasma density and cosmic ray flux, changing from one set of values to another. The most significant boundary crossing in the history of exploration announced through a spreadsheet. But for those who understood what it meant, for those who could feel the weight of it, the crossing of the heliopause was one of the most profound moments in the story of our species. Think about that for a moment. A machine designed and built by human hands, powered by the slow decay of a few pounds of plutonium, guided by a computer with 69 kilobytes of memory, had traveled beyond the reach of the sun's wind and entered the space between the stars. For the first time in the history of our species, something we had made was touching the interstellar medium. Something we had built was swimming in the ocean between the suns. Let us sit with that for a moment. Let the quiet of it settle over you. Voyager 1, at this very moment, is drifting through interstellar space. The particles flowing past its instruments are not from our Sun. They are from other stars, from supernovae that exploded millions of years ago. From the diffuse gas that permeates the galaxy, the thin, cold medium that fills the enormous spaces between stellar systems. Voyager is immersed in the stuff of the galaxy itself. And yet, as we said, Voyager has not left the solar system, not by the gravitational definition. The Oort cloud, that vast, distant reservoir of icy bodies, still lies ahead. The Sun's gravitational influence still holds Voyager in its gentle embrace, slowing it down by an imperceptible amount with each passing moment. Voyager is moving fast enough to escape the Sun's gravity entirely. Its velocity exceeds the solar escape velocity at its current distance. It will never fall back. It will never return. But the Sun's gravity is still there. A whisper, a thread, growing thinner and thinner, but never quite breaking, like the memory of a parent's voice fading as you walk further from home. The Oort cloud is believed to extend from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. Voyager 1 is currently at about 165 astronomical units. At its current speed, it will reach the odd, inner edge of the Oort cloud in roughly 300 years, and it will spend perhaps 30,000 years crossing through it, through that vast, sparse halo of icy bodies, each one a frozen relic from the formation of the solar system 4.5 billion years ago. The Oort cloud is so diffuse, so thinly populated, that the chance of Voyager actually hitting one of these icy bodies is essentially zero. There are estimated to be trillions of objects in the Oort cloud, but they are spread across a volume so enormous that the average distance between them is measured in millions of miles. Voyager will pass through the Oort cloud the way a single dust mote passes through an empty cathedral. The odds of an encounter are vanishingly small, but the Oort cloud itself is worth a moment of contemplation. We have never seen it. No telescope has ever photographed an Oort cloud object in place. Its existence is inferred from the orbits of long-period comets, those spectacular visitors, that appear in our inner solar system every few centuries or millennia, trailing tails of gas and dust as they are warmed by the Sun for the first time in billions of years. These comets come from somewhere. Their orbits, traced backward, point to a vast spherical reservoir surrounding the Sun at enormous distances. A halo of trillions of frozen bodies, each one a relic from the solar system's formation. Each one a snowball of ice and dust that has been drifting in the dark since before the first life stirred on Earth. The Oort cloud is the Sun's most distant possession, its outermost suburbs, the last, thinnest thread connecting our star to its gravitational territory. And Voyager 1 will pass through it like a fish swimming through an empty ocean, surrounded by water, but seeing nothing, touching nothing, encountering nothing but the vast, patient silence of the deep. And then, after perhaps 30,000 years, Voyager will emerge from the Oort cloud's outer edge. And at that point, finally, it will truly be free. Free of the Sun's gravity, free of the solar system, alone in interstellar space, with nothing ahead of it but the vast, empty gulf between the stars. And now, at last, we can ask the question that brought us here tonight, the question that stretches the imagination beyond anything we have considered so far. Where will Voyager 1 be in 1 million years? Close your eyes. Take a slow breath. and let us follow a small machine into the deepest future we can imagine. Section 5. 1 million years. 1 million years. Say it slowly. Let it sit in your mind like a stone dropped into still water. 1 million years. It is a number we use casually, a number that appears in science articles and history books and conversation. But it is not a number that the human mind can truly comprehend. We can write it down. We can do arithmetic with it, but we cannot feel it. We cannot hold it. It exceeds the capacity of our imagination in the same way that the distance to the stars exceeds the capacity of our intuition for space. 1 million years ago, the species Homo sapiens did not exist. Our ancestors were Homo erectus, or perhaps early members of the lineage that would eventually produce us. They lived in Africa and parts of Asia. They used fire. They made simple stone tools. They did not have language, at least not in any form we would recognize. They had never seen a wheel, a boat, a written word, a city, a farm, a piece of music. Everything that defines human civilization, everything that separates us from the other animals, everything that makes you you, happened in the last fraction of 1 million years. The last 10%, the last 5%, the last 1/10 of 1% if we are talking about recorded history. And we are asking where a machine will be in that same span of time, 1 million years from now, into a future as unimaginably distant from us as those stone tool-wielding ancestors are unimaginably distant from us in the past. Let us start with the math, because the math, in this case, is the surest ground we have. Everything else, the speculation about stellar encounters, about galactic orbits, about what will happen to the spacecraft itself, all of that rests on assumptions and models that may or may not be accurate over such vast timescales. But the basic physics of motion is reliable. If we know how fast something is going and what direction it is headed, we can calculate where it will be at any point in the future, at least in principle. Voyager 1 is traveling at approximately 17 kilometers per second relative to the Sun. That is roughly 10.5 miles per second, or about 38,000 miles per hour. This speed is not changing significantly. There is essentially no drag in interstellar space, no friction, no resistance. The only force acting on Voyager is gravity, primarily from the Sun, but also from the galaxy as a whole, and these gravitational influences are too weak at Voyager's distance to produce any meaningful change in speed over the timescales we are considering. For all practical purposes, Voyager 1 will maintain this speed indefinitely. Let us work out the distance, 17 kilometers per second. Over 1 year, that translates to roughly 536 million kilometers. Over 1,000 years, roughly 536 billion kilometers. Over 1 million years, roughly 536 trillion kilometers. To convert that into more familiar units, 1 light year is approximately 9.46 trillion kilometers. So, in 1 million years, Voyager 1 will have traveled roughly 56,700 light years from the Sun. Let that number settle. 56,700 light years. That number is so large that it almost refuses to mean anything. Let us try to find some footholds, some handholds, some way to grasp the scale of what we are talking about. If you sent a radio signal from Earth right now, traveling at the speed of light, the fastest speed anything in the universe can achieve, it would take 56,700 years to reach the point where Voyager 1 will be in 1 million years. That is longer than all of recorded human civilization, longer than agriculture, longer than the oldest cave paintings. A message sent today would not arrive until a time so distant that the human species may have evolved into something entirely different, or vanished altogether. And here is the thing that makes this number truly breathtaking. Voyager is not traveling at anything close to the speed of light. It is traveling at roughly 1/18,000th of the speed of light. So, the distance Voyager covers in 1 million years at its relatively modest speed is the same distance that light would cover in 56,700 years. The ratio between Voyager's speed and the speed of light is the ratio between a crawl and a sprint, stretched across geological timescales until even the crawl adds up to an extraordinary distance. To put that distance in perspective, let us think about the size of our galaxy. The Milky Way is a barred spiral galaxy with a diameter of roughly 100,000 light-years. Our Sun sits about 26,000 light-years from the galactic center, roughly 2/3 of the way out from the center to the edge. The galaxy is a vast, flat disk of stars, gas, and dust, with a bulge at the center and sweeping spiral arms that curve outward like the arms of a pinwheel. In 1 million years, Voyager 1 will have traveled roughly 56,700 light-years. That is more than half the diameter of the entire Milky Way galaxy. If you could somehow hover above the galaxy and look down, and if you could see Voyager 1 as a tiny dot moving outward from the Sun's position, after 1 million years that dot would have crossed an enormous swath of the galactic disk. It would have passed through, or near, thousands of star systems. It would have traversed spiral arms and the dark spaces between them. It would be in an entirely different part of the galaxy, surrounded by stars that are invisible from Earth, stars that have never been named, stars that our telescopes have never recorded. Of course, this simple calculation assumes that Voyager is traveling in a straight line at constant speed. And over 1 million years, that assumption breaks down. Voyager 1 is not just a projectile flying through empty space. It is a tiny piece of matter embedded in a galaxy, and the galaxy has gravity. Every star, every cloud of gas, every dark matter halo exerts a gravitational pull on everything around it. Over thousands and millions of years, these gravitational influences will subtly bend Voyager's trajectory, curving its path, altering its speed, pulling it this way and that like a leaf on a slow, vast river. The most significant gravitational influence on Voyager's long-term trajectory is the Milky Way itself. Our galaxy is not just a collection of stars. It is a gravitational system, a coherent structure held together by the combined gravity of all its stars, gas, and dark matter. Everything in the galaxy, including our Sun and including Voyager 1, orbits the galactic center. The Sun takes roughly 230 million years to complete one orbit. Voyager 1, once it is free of the Sun's gravity, will follow its own orbit around the galactic center, an orbit determined by its speed, its direction, and the gravitational field of the galaxy. Over 1 million years, Voyager will complete only a tiny fraction of a galactic orbit. 230 million years for one orbit means that in 1 million years, Voyager moves through roughly 1/230th of its orbit, less than half a degree, a barely perceptible arc. But even that tiny arc means that Voyager's trajectory is not a straight line. It is a very gentle curve, bending slowly toward the galactic center under the influence of the galaxy's gravity. But long before Voyager completes any meaningful fraction of its galactic orbit, something else will happen. something that brings the abstraction of these enormous distances and timescales into a sharp, specific focus. Voyager 1 will pass near other stars, not collide with them. The chance of Voyager actually hitting a star is so small as to be effectively zero. Stars are tiny compared to the distances between them. If you could shrink the sun to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. The galaxy is overwhelmingly empty. Voyager could fly through it for trillions of years and never hit anything larger than a dust grain. But it will pass through stellar neighborhoods. It will enter the gravitational influence of other suns. And the first significant stellar encounter is not as far away as you might think. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. This is a small, dim star, a red dwarf with roughly 0.42 solar masses, located in the constellation Camelopardalis, Q Mel Opar Du Lis, the giraffe. It is currently about 17.6 light-years from Earth, but it is moving toward us at a significant speed. In about 40,000 years, it will be the closest star to our Sun, closer even than Proxima Centauri is today. Voyager 1's trajectory happens to take it in the general direction of Gliese 445. The spacecraft will not approach the star closely enough to be captured by its gravity. 1.6 light-years is still an enormous distance, roughly 10 trillion kilometers. But by stellar standards, it is a reasonably close pass. Close enough that if any civilization existed around Gliese 445 and had sufficiently advanced telescopes, they might, in principle, detect the presence of a small artificial object passing through their outer stellar neighborhood. They would not see it, of course. Voyager 1 is far too small and far too dim to be detected optically at interstellar distances. But they might detect the faint radio emissions from its transmitter if the transmitter were still operating, which it will not be, of course. Voyager's transmitter will have fallen silent more than 39,000 years before the Gliese 445 encounter. So even this close pass will occur in silence. Voyager will glide past Gliese 445 like a bottle drifting past an island in the night, unseen and unheard. Think about that encounter for a moment. 40,000 years from now. That is roughly twice the span of time since the last ice age, since woolly mammoths roamed the earth and human beings painted bison on cave walls in southern France. Double that span. Project it forward. And, at the end of it, Voyager 1 will be flying past a star. What will be happening on Earth in 40,000 years? No one can say. We cannot predict what will happen next year with any reliability, let alone in 40 millennia. Civilizations may have risen and fallen a dozen times. Humanity may have spread to other worlds. We may have engineered our own evolution, becoming something unrecognizable. Or we may be gone entirely. Our cities crumbled to dust, our species extinct, our planet carrying no memory of us except fossils in the rock and a faint, anomalous signature of industrial pollution in a thin geological stratum. But Voyager 1 will still be there, still moving, still carrying its golden record, passing through the neighborhood of a star that the people who built it never knew would be important. A star that would not become the Sun's nearest neighbor for another 40,000 years. The irony is almost poetic. Voyager is flying toward a rendezvous that was written in the motions of the stars, a meeting that was determined not by human planning but by galactic dynamics, by the slow, majestic drift of suns through the galaxy. The stars are moving. The sun is moving. Gliese 445 is moving, and Voyager is moving, and their paths, traced forward through time, converge in the darkness of the far future, for a meeting that neither side will notice. After Gliese 445, Voyager will continue onward, deeper into the galaxy. And here is where the story becomes increasingly speculative, because predicting Voyager's trajectory over hundreds of thousands of years requires knowing the positions and motions of billions of stars. And our knowledge of the galaxy is not nearly detailed enough for that level of precision. We know the general direction Voyager is heading. We know its speed. We can calculate its approximate position at various times in the future. But the exact sequence of stellar encounters, the precise gravitational perturbations from passing stars and gas clouds, the detailed path through the galaxy's gravitational field, all of these become increasingly uncertain as we project farther into the future. What we can say with confidence is that over 1 million years, Voyager 1 will pass through or near many star systems. The average distance between stars in our region of the galaxy is roughly 4 to 5 light years. Voyager, traveling at 17 kilometers per second, covers about 1 light year every approximately 17,600 years. Over 1 million years, that is roughly 57 light years of travel, which means Voyager will pass through roughly 11 or 12 stellar neighborhoods, if we define a neighborhood as the region within a light year or two of a star. Most of these stars will be ordinary. Red dwarfs, the most common type of star in the galaxy, making up roughly 70 to 80% of all stars. Some might be sun-like stars. A few might be binary systems or even systems with known planets. None of them will capture Voyager. The gravitational pull required to capture an object moving at 17 kilometers per second would require an extraordinarily close approach to a very massive object, and the probability of such an approach is vanishingly small. Instead, each stellar encounter will give Voyager a tiny gravitational nudge, a slight change in direction, a minuscule change in speed. These nudges will accumulate over time, gradually, altering Voyager's trajectory in ways that are impossible to predict with precision. Over millions of years, Voyager's path will become increasingly chaotic, not in the sense of wild or erratic, but in the mathematical sense. Sensitive to initial conditions and impossible to predict exactly beyond a certain time horizon. There is something profound in that unpredictability, something almost philosophical. We built this machine. We chose its trajectory. We aimed it at Jupiter and Saturn with exquisite precision, calculating its path to fractions of a degree. And now, projected forward through time, our precision dissolves. The careful aim becomes an approximation. The calculated trajectory becomes a cloud of possibilities, widening with every 1,000 years, until after 1 million years we simply do not know where it will be. Not exactly, not precisely. We know the general region, we know the approximate distance, but the exact location, the exact star it will be nearest to, the exact direction it will be heading, all of that is lost in the fog of gravitational complexity. We launched it with certainty. It will arrive wherever it arrives with mystery. The machine that was once the most precisely tracked object in the solar system will become, over cosmic timescales, the most untraceable. And perhaps that is appropriate. Perhaps it is fitting that a message meant for the unknown should itself become unknown. That a letter thrown into the cosmic ocean should eventually lose its return address. And what about Voyager itself? What will happen to the physical spacecraft over 1 million years? This is a question that ventures into territory where we have no direct experience. No human-made object has ever endured for 1 million years. The oldest artifacts of our species, stone tools, cave paintings, are at most a few 100,000 years old, and they have survived only because they were made of durable, inert materials and protected by caves or sediment from the worst of the elements. Voyager is made of aluminum, titanium, glass, silicon, plutonium, and 1,000 other materials, and it is exposed to the raw environment of interstellar space. That environment is, in some ways, surprisingly benign. There is essentially no atmosphere to cause corrosion, no weather, no water, no oxygen. The primary threats are radiation, cosmic dust impacts, and the slow degradation of materials in a vacuum. Cosmic rays, high-energy particles from distant supernovae and other energetic events, will bombard Voyager continuously. Over thousands of years, this radiation will gradually damage the spacecraft's electronics, altering the structure of its silicon chips, degrading its wiring insulation, and weakening its structural materials. But these changes will be slow, incremental, and largely irrelevant to a spacecraft that has already lost power and ceased functioning. Dust grain impacts are a more immediate physical threat, though immediate is relative when we are talking about 1 million years. Interstellar space is not perfectly empty. It contains a thin scattering of gas atoms and tiny dust grains, primarily silicate and carbon particles, with sizes ranging from a few nanometers to a few micrometers. These grains are incredibly sparse, with densities of perhaps 1 grain per cubic kilometer or even less. But Voyager is moving through this medium at 17 kilometers per second, and at that speed, even a microscopic grain of dust carries significant kinetic energy. Scientists have estimated the collision rate and concluded that over 1 million years, Voyager will be struck by numerous dust grains, but the vast majority will be too small to cause significant damage. The cumulative effect will be a slow, gentle sandblasting of the spacecraft's surface, a gradual erosion that will pit and roughen the metal, cloud the glass of the camera lenses, and wear away the thinnest and most delicate components. But the bulk, structure of the spacecraft, the aluminum frame, the titanium bolts, the gold-plated copper of the golden record, should survive largely intact. Metal does not rot in a vacuum. It does not rust without oxygen. It does not decay the way organic materials do. The most vulnerable component may be the spacecraft's thermal blankets, the multi-layer insulation that wraps much of Voyager's body. These blankets are made of thin sheets of mylar and captain, held together with adhesives and stitching. Over hundreds of thousands of years, cosmic ray bombardment will break down the polymer chains in these materials, making them brittle and fragile. The blankets may eventually crack and flake away, exposing the underlying structure. But the structure itself will endure. There is a peculiar comfort in that durability. In a universe where everything changes, where stars are born and die, where galaxies collide and reform, where even the protons in your body may eventually decay given enough time, a small machine made of aluminum and titanium will persist. Not because it is special, not because it is protected, but because the environment of interstellar space is so empty, so devoid of the forces that destroy things on Earth, that objects placed in it are effectively preserved forever, or at least for timescales so long that the word forever starts to feel almost appropriate. On Earth, everything decays. Wood rots, Iron rusts. Stone crumbles. Even mountains are worn down by wind and rain and the slow, patient grinding of glaciers. Nothing lasts. Nothing endures. But in space, where there is no air, no water, no weather, no biology, the rules are different. An aluminum frame does not corrode in a vacuum. A titanium bolt does not weaken without moisture. A gold-plated copper record does not tarnish without an atmosphere. The things that destroy objects on Earth simply do not exist in interstellar space. This is the paradox of Voyager's environment. The same emptiness that makes interstellar space so hostile to life makes it a perfect museum. A place where artifacts are preserved not for centuries, but for eons. A place where a small machine from a small planet can endure long enough for the stars themselves to rearrange around it. After 1,000,000 years, what will remain of Voyager 1? The RTGs will be long dead. The plutonium-238, with its half-life of 87.7 years, will have decayed through more than 11,000 half-lives. The radioactive material will have been transformed almost entirely into stable isotopes, retaining no significant radioactivity. The thermoelectric generators will be inert, cold, producing no power. The electronics will be non-functional, their silicon chips degraded by cosmic radiation, their wiring corroded by slow atomic-level processes. The cameras will be blind. The radio will be silent. The computers will be dead. But the structure will survive. The aluminum frame. The titanium bolts. The antenna dish. The instrument booms. Scarred and pitted by 1,000,000 years of micrometeorite impacts, stripped of its thermal blankets, darkened and worn, but recognizable. Still a machine. Still clearly artificial. Still bearing the unmistakable signature of intelligent design. And, on one side of the spacecraft, mounted on a bracket and protected by a metal cover, a 12-inch golden disc will still be there. Slightly worn, perhaps, its surface marked by the faintest traces of interstellar erosion, but intact. Readable. Waiting. The golden record. Let us pause here. Let us sit with this image for a moment, the way you might sit at a window on a quiet evening, watching the last light fade from the sky. 1,000,000 years from now, a small, battered machine will be drifting through a part of the galaxy we have never mapped, surrounded by stars we have never named. Its cameras will be blind. Its radio will be silent. Its computers will be dark. It will have no way of knowing where it is, or that it was ever anywhere else. It will carry no memory of its journey, no record of the storms of Jupiter, or the rings of Saturn, or the pale blue dot that was its home. Those memories exist only in the data it sent back. Data stored on servers on a planet that may or may not still exist. But the golden record will remain. A 12-inch circle of gold-plated copper, engraved with instructions that no human will ever read, carrying sounds that no human will ever hear again in that form. It is the most patient artifact ever created. It was designed to wait, and it will wait for as long as it takes, for 1,000,000 years, for 1,000,000,000, for longer than that. What a remarkable thing to build. What a remarkable thing to send into the dark. Section 6. The Golden Record. Let us slow down here. Let us take our time with this part of the story. Because the Golden Record is not just a piece of hardware. It is not just a data storage device. It is a message, a love letter, a portrait of a species that looked up at the stars and said, "We were here." The story of the Golden Record begins with a man named Carl Sagan. We mentioned him earlier in the context of the pale blue dot photograph. Sagan was an astronomer, a planetary scientist, a writer, and one of the most gifted science communicators who ever lived. He had a rare ability to see the cosmic significance in things that others treated as routine. Where other scientists saw a spacecraft, Sagan saw a messenger. Where others saw a launch, Sagan saw a farewell. In 1976, as the Voyager spacecraft were being assembled at the Jet Propulsion Laboratory, NASA asked Sagan to chair a committee tasked with creating a message that could be carried aboard the spacecraft into interstellar space. A message that would represent Earth and its inhabitants to anyone or anything that might find the spacecraft millions of years from now. Sagan took the assignment seriously, more than seriously. He treated it as one of the most important tasks he had ever been given, because he understood, perhaps more clearly than anyone, what Voyager's journey meant. These spacecraft were going to outlast everything, every building, every bridge, every monument, every city, every nation, every civilization that had ever existed or would ever exist on Earth. When the last human has died, when the last trace of our species has crumbled to dust, when the Earth itself has been swallowed by the expanding sun 5 billion years from now, the Voyager spacecraft will still be out there, drifting, intact, carrying whatever message we chose to put on them. Sagan assembled a small committee that included the writer Anne Druyan, who would later become his wife, the artist, John Lomberg, the physicist Frank Drake, the journalist Timothy Ferris, and several others. They had only about 6 weeks to complete the project. 6 weeks to compose a message that would need to be intelligible to a completely alien intelligence, with no shared language, no shared biology, no shared frame of reference. They chose a golden phonograph record, a 12-inch disc made of gold-plated copper, enclosed in a protective aluminum cover. The record would be played at 16 2/3 revolutions per minute, and it would contain both sounds and images, encoded as analog audio signals that could be decoded using instructions engraved on the record's cover. The choice of a phonograph record might seem quaint today, in an age of digital streaming and solid-state memory. But it was, in fact, an inspired decision. A phonograph record is an analog medium. The information is stored physically, as grooves in a surface, not as magnetic states or electronic charges that can be erased by radiation or lost to degradation. As long as the grooves survive, the information survives. And in the vacuum of space, where there is nothing to scratch the record, nothing to warp it, nothing to corrode it, the grooves will survive for a very, very long time. A digital recording might become unreadable in centuries as the medium degrades. The golden record will be readable in millions of years. There is something beautifully appropriate about that. A technology that was already becoming obsolete on Earth in 1977, superseded by cassette tapes and soon by compact discs, turned out to be the perfect medium for interstellar communication. Simple, durable, self-explanatory, a groove in a surface. Even without the instructions on the cover, a sufficiently intelligent finder might deduce that the grooves contain information, simply by examining them under magnification and noticing their regularity, their structure, their clear departure from anything that nature produces. The contents of the Golden Record are a time capsule of life on Earth in 1977. They are eclectic, poignant, sometimes puzzling, and deeply human. The record contains 115 images, encoded as analog signals. These images include photographs of the solar system, of Earth's surface, of human anatomy, of cells and DNA, of animals and plants and insects and fish. There are photographs of humans eating, drinking, nursing babies, a woman licking an ice cream cone, a man carrying a child on his shoulders, a family gathered around a dinner table. There are diagrams showing the structure of DNA, the solar system, the composition of the Earth's atmosphere, and the mathematics of chemistry. The record contains spoken greetings in 55 languages, ancient and modern. Akkadian, Ukai Di Un, the language of ancient Sumeria. Mandarin Chinese, Hindi, Arabic, English, Swahili. A greeting in Amoy, a Chinese dialect that says, "Friends of space, how are you all? Have you eaten yet? Come visit us if you have time." A greeting in English by Nick Sagan, Carl Sagan's 6-year-old son, that says, "Hello from the children of planet Earth." The record contains a sound essay, a 12-minute montage of the sounds of Earth, the rumble of a volcano, the crash of thunder, the sound of wind and rain and surf, a heartbeat, laughter, the cry of a newborn baby, the bark of a dog, the song of a whale, a train, a tractor, a jet airplane, an elephant, a chimpanzee, the sounds of a kiss, and the record contains music. 27 musical selections from around the world, spanning thousands of years of human creativity. Bach's Brandenburg Concerto No. 2, Beethoven's Fifth Symphony, First Movement, Mozart's Magic Flute, Queen of the Night aria, Louis Armstrong singing Melancholy Baby, Chuck Berry's Johnny B. Good, a Navajo night chant, a Peruvian wedding song, Indian raga, Javanese gamelan, Senegalese percussion, Georgian choral, singing, a song by the Pygmies of the Ituri Rainforest. The committee agonized over every choice. Every song included meant a song excluded. Every image selected meant an image left behind. How do you represent an entire planet in 115 photographs? How do you capture the richness of human music in 90 minutes of audio? How do you say everything that needs to be said to an audience that may not even have ears? There were debates. Passionate debates. The Beatles wanted to include Here Comes the Sun, but their record label, EMI, refused to grant the rights for an Interstellar release. It is one of the small, absurd footnotes of the Golden Record project that a record company worried about copyright infringement in deep space. As if an alien civilization, having traveled across the galaxy to retrieve a small golden disk from a dead spacecraft, would then illegally distribute Beatles songs without paying royalties. There were also deliberate choices that reveal the committee's philosophy. The images include no depictions of war, violence, or poverty. There are no photographs of weapons or armies or disease. The Golden Record presents an idealized version of humanity, a portrait of a species at its best. This was intentional. Carl Sagan and his committee understood that they were not creating a documentary. They were creating a first impression. And they wanted that first impression to reflect the best of who we are, not the worst. Some have criticized this choice. They argue that the Golden Record presents a misleadingly rosy picture of life on Earth, omitting the suffering and the cruelty that are as much a part of the human story as the music and the laughter. And perhaps they have a point. But there is also something touching about the impulse. When you are sending a message to the stars, when you are introducing yourself to the universe, you put on your best clothes. You bring your best wine. You play your finest music. You show the version of yourself that you wish you were. And in doing so, you reveal something true about who you actually are. A species that aspires. A species that knows the difference between what it is and what it wants to be. There is a detail about the golden record that most people do not know, a detail that transforms it from a scientific artifact into something deeply personal. At the very end of the recording process, Anne Druyan's brainwaves were recorded using an EEG, an electroencephalogram. She sat quietly for an hour while the machine recorded the electrical activity of her brain, and those signals were pressed into the record along with everything else. What Anne Druyan was thinking about during that hour she has described many times. She was thinking about the history of Earth, about the rise and fall of civilizations, about the violence and the beauty, about war and love and suffering and hope. And she was thinking about Carl Sagan, because 2 days before her brain, waves were recorded. She and Carl had declared their love for each other. They had been friends and colleagues for years, but in that moment, on a phone call that lasted hours, something shifted. They fell in love. So encoded in the golden record, pressed into gold-plated copper and launched into interstellar space, are the brainwaves of a woman newly in love. The electrical signature of joy and wonder and tenderness and fear and hope, all tangled together, all utterly human, all riding on a spacecraft toward the stars. It is, perhaps, the most human artifact ever created. Not the computer, not the antenna, not the nuclear generator, but a phonograph record carrying the sound of whales and the music of Bach and the brainwaves of a woman in love, hurtling through the darkness at 10.5 miles per second, growing farther from home with every passing moment, carrying the message that we existed and that we cared enough to say so. The cover of the golden record is engraved with diagrams designed to help an alien civilization play the record. These diagrams include a representation of the hydrogen atom, the most common element in the universe, using the spin-flip transition of hydrogen as a basic unit of time and length. The diagrams show how to extract the record from its cover, how to place the stylus, how to set the correct rotational speed, and how to decode the video images from the audio signal. There is also a pulsar map, similar to the one included on the Pioneer plaques that were launched on earlier spacecraft. The map shows the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars that emit beams of radio waves at very precise frequencies. Each pulsar is labeled with its rotational period, providing a kind of cosmic GPS that would allow the finder to determine where the Sun is located in the galaxy, and by accounting for the gradual slowing of the pulsar's rotation rates when the spacecraft was launched. It is a map that points to home, written in the language of physics, the one language that any sufficiently advanced civilization should be able to read. But here is the question that haunts anyone who thinks carefully about the golden record. Will anyone ever find it? The honest answer, the one that scientists give when pressed, is almost certainly not. The chance of the golden record being found by an alien civilization is so small as to be effectively zero, at least in any foreseeable time frame. Consider the numbers. Voyager 1 is roughly the size of a small car. It is traveling through a galaxy that contains somewhere between 100 billion and 400 billion stars, spread across a disk 100,000 light-years in diameter. The average distance between stars in our region of the galaxy is about 4 to 5 light-years. Voyager emits no light, no heat, no radio signal. It is, for all practical purposes, invisible. A grain of sand drifting through an ocean, the size of the Pacific. Even if an advanced civilization existed at one of the stars Voyager will pass near in the next 1,000,000 years, they would need extraordinarily sensitive instruments to detect an object this small and this faint. They would need to be looking in exactly the right direction at exactly the right time. They would need to be searching for exactly this kind of thing, an artificial object the size of a refrigerator, drifting silently through their outer stellar neighborhood at 17 kilometers per second. The probability is not zero. In an infinite universe, very little is truly impossible. But it is so small that Carl Sagan himself, the man who championed the golden record, acknowledged that it was unlikely to ever be found. The golden record, he said, was more like a message thrown into the ocean than a letter mailed to a specific address. The value of the message was not in the likelihood of its being received. The value was in the fact that we sent it. And yet, there is another way to think about it. The golden record does not need to be found by aliens in order to have served its purpose. It has already served its purpose. It served its purpose the moment it was created. Because the act of making the golden record forced a small group of human beings to sit down and ask, what are we? What matters about us? What would we want to say to the universe if we could only say one thing? And the answers they came up with, the music and the photographs and the greetings and the sounds of rain and whales and laughter, those answers are a mirror. They reflect back to us a vision of ourselves that is both humbling and inspiring. We are small. We are brief. We are confined to a tiny planet orbiting an ordinary star. But we have Bach. We have laughter. We have rain. We have love. And we thought those things were worth sending to the stars. That is the real message of the golden record. Not the one encoded in its grooves, but the one encoded in its existence. And perhaps that is the point. Perhaps the golden record was never really for them. Perhaps it was always for us. Think about what it means that a species, barely a few thousand years into its technological history, looked up at the vastness of interstellar space and said, "We should say something. We should leave a record. We should put our best foot forward, select our most beautiful music, capture the sounds of our world, and send it all into the darkness on the chance, the infinitesimally small chance that someone might find it someday." That is not a scientific act. It is an act of faith, an act of hope, an act of love for a future that the sender will never see. The golden record tells us more about who we are than any finder could ever learn from it. It tells us that we are a species that dreams, a species that reaches beyond what is necessary, beyond what is practical, beyond what makes sense. A species that sends music to the stars, not because anyone will hear it, but because not sending it would feel like a betrayal of who we are. Section 7. A Message in a Bottle. Let us return, one last time, to the quiet of the present moment. You are lying in bed. The room is dark. The world outside your window is still, or nearly so. And somewhere out there, beyond the rooftops, beyond the clouds, beyond the atmosphere, beyond the moon and Mars and Jupiter and Saturn, and the icy objects at the edge of the solar system, beyond the heliopause where the sun's wind gives way to the interstellar medium, a small machine is flying through the dark. It is not thinking, it is not feeling. It has no consciousness, no awareness, no sense of where it is or where it is going. It is a collection of metal and silicon and glass and gold, assembled by human hands in a room in California nearly 50 years ago, and it is doing the only thing it can do. It is moving forward. Throughout all of human history, we have been sending things into the unknown. Long before Voyager, long before rockets, long before telescopes, we have been throwing messages into the dark and hoping someone would find them. every ship that sailed beyond the horizon, every signal fire lit on a distant hill, every word written in a language that the writer knew might someday die. We are, at our core, a species that cannot bear to be alone, a species that reaches out again and again, even when there is no one there to reach back. Voyager 1 is the purest expression of that impulse. A message in a bottle thrown into an ocean so vast that the bottle may drift for 1 billion years without touching shore. And yet we threw it anyway. We threw it because that is what we do. Because silence, for us, is not an option. Let us trace the timeline forward, one more time, slowly and gently, like tracing a path on a map with your fingertip. Let us follow Voyager 1 into the deep future, marking the milestones along the way, watching the distances grow and the silence deepen. In roughly 10 years from now, give or take a few years, the last instrument aboard Voyager 1 will be shut down. The power from the RTGs will drop below the threshold needed to run even the most essential systems. The transmitter will send its last signal, a final whisper of data, and then go silent. On Earth, the engineers at the Jet Propulsion Laboratory will note the time, the date, the last telemetry reading. Perhaps they will gather in a room and raise a glass to a machine that exceeded every expectation, that outlived every prediction, that worked for decades longer than it was designed to work. And then they will turn off the receivers and the connection will be severed. For the first time in nearly 6 decades, Voyager 1 will be truly alone. In 1,000 years, Voyager will be roughly 0.06 light-years from the Sun, still within the Oort cloud, still technically within the solar system by the gravitational definition, but so far from anything recognizable that the distinction between inside and outside will have lost all meaning. In 10,000 years, Voyager will be roughly 0.6 light-years from the Sun. It will have crossed the inner Oort cloud and will be deep within the outer halo of icy bodies that marks the gravitational frontier of our star. In 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445. It will not stop. It cannot stop. It will fly past that small red star the way a leaf flies past a window in a storm, too fast and too distant and too silent to be noticed. And then it will continue on, deeper into the galaxy, past stars that do not yet have names, through regions of space that no telescope has ever mapped. In 100,000 years, Voyager will be roughly 5,700 light-years from Earth. The solar system will be a memory. The sun will still be shining, still warming the Earth, still sustaining whatever life remains on its third planet. But Voyager will be so far away that the sun will be invisible to the naked eye, even if there were eyes to see it. Just another star among billions, lost in the vast, glittering sweep of the Milky Way. In 500,000 years, Voyager will have traveled roughly 28,000 light-years. It will have crossed a significant fraction of the galactic disk. The star patterns in its sky, if it had a sky, would be unrecognizable. Every constellation would be different. Every familiar reference point would be gone. The spacecraft would be adrift in a region of the galaxy that has no connection to its origin, no relationship to the solar system, no memory of a small blue world orbiting a yellow sun. And in 1 million years, Voyager 1 will be roughly 56,700 light-years from where it started, more than half the diameter of the galaxy. It will have passed through or near dozens of star systems. Its surface will be pitted and worn by a million years of micrometeorite impacts. Its thermal blankets will have disintegrated. Its instruments will be dead, its computers dark, its radio silent. But its structure will survive. Aluminum and titanium do not decay in the vacuum of space. Gold does not corrode without oxygen and water. The golden record, protected by its metal cover, will be largely intact. Still readable. Still carrying its cargo of music and images and greetings and brainwaves. Still waiting with infinite patience for someone to pick it up and listen. And beyond 1 million years? What then? The answer is that Voyager's journey does not end at 1 million years. That is just an arbitrary milestone, a number we chose because it sounds significant, because it is round and large and makes us catch our breath. But there is nothing special about the 1 million-year mark. Voyager will not stop there. It will not arrive anywhere. It will simply keep going. In 10 million years, Voyager will have traveled roughly 567,000 light years. That is well beyond the Milky Way galaxy itself. But wait, that simple calculation assumes straight-line travel at constant speed, and over 10 million years, the galaxy's gravity will have dramatically curved Voyager's path. Voyager will still be within the Milky Way, orbiting the galactic center on its own independent orbit, a tiny piece of metal circling a galaxy of 400 billion stars, unattached to any one of them, a permanent nomad. In 1 billion years, the calculation becomes even more uncertain. The galaxy itself will have changed. Stars will have been born and died. The sun will still be shining, but it will be significantly hotter, and the Earth's oceans may have begun to evaporate. The continents will have merged and separated and merged again, and Voyager will still be out there, still drifting, still carrying its record, indifferent to the passage of time, because time, for a machine in a vacuum, passes without consequence. In 5 billion years, the sun will die. It will swell into a red giant, engulfing the inner planets, and then shed its outer layers, collapsing into a white dwarf. The solar system as we know it will cease to exist, and Voyager, somewhere in the galaxy, separated from its home star by billions of years and trillions of miles, will not notice. It will feel no tremor. No signal will reach it. The death of the sun will be an event that occurs in a different part of the galaxy, irrelevant to a small machine that left home a very long time ago. Let us think about what it means to create something that outlasts everything, not just outlasts you or your children or your civilization, but outlasts your species, outlasts your planet, outlasts the very star that warmed the world where you were born. The Voyager spacecraft will outlast all of it. The spacecraft will still be drifting through the galaxy long after the sun has exhausted its hydrogen fuel and swelled into a red giant, swallowing Mercury and Venus and perhaps the Earth. Long after the red giant has shed its outer layers and collapsed into a white dwarf, a tiny, dense ember glowing faintly in the dark. Long after even the white dwarf has cooled and gone dark, becoming a black dwarf, a cold, dead cinder of a star that once gave warmth to a planet where music was written, and babies laughed and people fell in love. The Voyager spacecraft may be the last trace of us, the last physical evidence that humanity ever existed. Not our buildings, which will crumble. Not our books, which will rot. Not our digital records, which will degrade. Not even our fossils, which will eventually be recycled by the Earth's geology. The Voyager spacecraft, drifting in the cold, empty, timeless vacuum of interstellar space, preserved by the same conditions that make that vacuum so hostile to life, may be the most durable artifact our species ever produces. And this is where the story of Voyager 1 becomes something more than science. More than engineering. More than a mission with objectives and data returns and funding codes. This is where it becomes philosophy, where it becomes poetry, where it becomes a meditation on what it means to be a small, fragile, temporary species on a small, fragile, temporary world, looking up at a universe that is neither small nor fragile nor temporary, and choosing deliberately and with great care to say something. We are here. We were here. We existed. We loved. We wondered. We looked at the stars and asked questions that we knew we might never be able to answer. And we sent a golden record into the dark, carrying our music and our laughter and the sound of wind and rain and the beating of a human heart, because we wanted the universe to know. Not because we expected an answer, not because we thought anyone was listening, but because the act of sending the message was, in itself, an answer to the deepest question of all. Are we alone? We may never know. But the fact that we asked, the fact that we cared enough to ask, the fact that we built a machine and filled it with music and launched it into the infinite, suggests that whatever we are something worth remembering. Voyager 1 is out there right now, at this very moment. As you lie here, letting the weight of sleep settle over you like a warm blanket, as your breathing slows and your thoughts begin to blur at the edges, a small machine the size of a car is flying through interstellar space at 10.5 miles per second. It has been flying for nearly half a century. It will fly for another 1,000,000 years, and another 1,000,000 after that, and another. On and on, through the silence and the dark, until the stars themselves grow old and die, and new stars are born from their ashes, and those stars grow old and die in turn. And on one side of that machine, gleaming faintly in the starlight that fills the galaxy, a golden record turns in silence. It carries the sound of a mother singing to her child, the thunder of a summer storm, the cry of a humpback whale in the deep ocean, a song by Chuck Berry, a concerto by Bach, a greeting from a 6-year-old boy, and the brainwaves of a woman in love. It carries us, the best of us, the gentlest, most hopeful version of who we are, sent into the dark by a species that knew it might not last, but wanted to be remembered anyway. Let that thought carry you into sleep tonight. Let the image of a small golden record spinning silently through the starlight be the last thing in your mind as you drift away. There is something comforting in it, something warm. The idea that no matter what happens here, no matter what becomes of us, a piece of who we are is out there, moving forward, always forward, into the dark, into the light, into whatever comes next. Voyager 1 will be out there for a very long time, and tonight, as you sleep, it will have traveled another 900,000 miles deeper into the galaxy. By the time you wake up, it will be a little farther from home, a little closer to wherever it is going. A silent emissary from a world of oceans and mountains and music and dreams, carrying a message that says, simply, beautifully, quietly, we were here, and we wanted you to know. The stars are out tonight. You cannot see them, perhaps, from where you are lying, but they are there. They are always there. Above the roof, above the clouds, above the atmosphere. Thousands of them. Millions. Billions. An ocean of light scattered across a darkness so vast that no mind can hold it. and somewhere in that ocean, a small golden record is catching the light of a distant star, reflecting it back into the void. The record spins in silence. The grooves carry their cargo of sound and image and human thought, as they have for decades, as they will for millions of years more. And the spacecraft that carries it moves on, 10.5 miles deeper into the galaxy with every passing second, carrying the best of us into whatever comes next. Sleep well. The universe is large, and it is dark, and it is full of silence. But it is not empty. We put something out there. Something good, something true. Something that says, in every language we know and in languages we have not yet invented, that we were alive, and we marveled at the stars, and we were not afraid to send a little piece of ourselves into the unknown. That is enough. That is more than enough. That is everything. Good night.